Thank you, everyone. Today I'll be presenting our paper, Implementing the History Stack, a digital framework for circular building practices in bio-based construction. And this research is coming out of CETA, the Center for Information Technology and Architecture at the Royal Danish Academy in Copenhagen. This research is part of an EU-funded project called Eco-Metabolistic Architecture, which is led by Mette Vromskar-Thomsen, who you'll hear from in just a few minutes as the keynote. And our thesis is to design for and with bio-based materials, we must challenge the fundamental value proposition of architecture. Instead of predicating design on an idealization of permanence, we must expand our conceptual material lifespan and find new ways of engaging practices of maintenance and intervention. And shown here is a picture of one of the traditional seagrass thatch roof huts on the island of Læsø in Denmark. And this is an important motivating inspiration for us, in particular because of the way in which these roofs are constructed and continually repaired over years with the addition of new material organically where it's needed, when it's needed. Many of you may be familiar with this butterfly diagram coming from the MacArthur Foundation, illustrating some of the different nested cycles within a more circular sort of conception of our building economy. And this aims to address a world in which buildings don't experience a single life arc from design to demolition, but rather multiple successive and even parallel life cycles and so-called cascades as parts of the buildings come into disrepair and are refit, repaired, reused, recycled, or replaced. And our own research, in particular for this paper, attempts to apply that to the problem of a need for data that you can use in particular use cases that come into play in a circular paradigm. So traditionally, our built environment is very data intensive, but all of that data is being employed at the design and fabrication stage. We have elaborate digital twins of buildings as they're constructed, but then much of the time that data kind of goes into a dormant state. Maybe it comes back into play at the time of renovation or demolition, but quite often it's just relegated to the status of a fossil. So in this circular paradigm, the need arises for a unified source of data about any given built entity in order to inform repairs and renovations, energy performance assessments, or life cycle analyses, and also simply general understanding of the material's behavior. Hitherto, such data sources were mainly limited to design and construction documents, which are highly detailed but painstakingly compiled just once at the start of a built entity's life and then left largely untouched and unused, whereas a circular paradigm necessitates a much more dynamic model that can adapt throughout a built entity's life cycles. So many people are putting their brilliant minds to this task. I've mentioned building information modeling briefly, but the efforts are evolving, especially with the introduction of more and more language related to a circular economy in our industry. Some of these notable examples and parallel efforts include Madaster, which is short for material cadastre, sort of a material passport approach to building. iBroad, Extendo, Aldrin. Several of these are coming out of a more recent push through the European Commission since 2020 with the aim to establish what are called digital buildings logbooks, DBLs, which unlike BIM models and passports, material passports or renovation passports, these digital building logbooks aim to be a repository that can grow and change over time, which is beginning to get closer to our needs in a circular economy where buildings are not simply placed into the built environment and left static and unchanging forever, but continually repaired. But several of these have different shortcomings. Sorry, just to go back here. For instance, iBroad log is an approach to digital building logbooks, but unfortunately only focuses on single-family residences, whereas Aldrin's build log covers office buildings and hotels. And for instance, Extendo is more oriented towards the integration of energy performance certificates. So each of these different approaches so far has had a particular agenda, a particular angle, and what results is we have many different models that have a very siloed and compartmentalized sort of thinking about how to approach the problem of creating a digital building logbook. To give a practical example of a time when we needed to use data in this way in our own research, I give the example of our project RawLam and the subsequent project ReShelter. So RawLam was a small timber demonstrator structure that we eventually disassembled and reused components of in a later structure called ReShelter, also a timber structure. And it was composed of these computationally designed glue laminated elements. And we found that in the disassembly stage, our original fabrication models, though they were highly accurate, were no longer relevant because these had changed throughout their lifespan. So we just geometrically alone, they'd already changed, let alone the material composition of the wood and the glue within. So in order to be able to effectively reuse these materials, we had to rescan them using a combination of different 3D scanners, both mobile phone-based LiDAR scanners, but also laser scanners. And this begins to show why we would need to have a continually updated store of information about any built entity. The fabrication model alone is not going to be sufficient for many of the renovation and repair use cases that we're going to see more and more of, hopefully, in a more circular building economy. But CETA goes beyond this to conduct some more radical explorations of the role of architectural maintenance in the application of biodegradable biopolymer 3D printed components. So in our lab, we've developed, in collaboration with Ariana Rick and Anders Dogard of DTU, a family of 3D printed biopolymers. And these aim to use all bio-based and waste stream based material sources. So for instance, the binders could be xanthan gum, or more recently we've been exploring more collagen glue. The latter is taken from waste products of the meat industry. And then the fillers, which can determine all sorts of aspects of the material, of course, from color to physical performance, could include things like paper flock from recycling of newspapers and books, cotton from jeans, bark, sugarcane, and hemp from agricultural wastes, and seagrass, and reference back to those thatch roof huts of Lesse. The aim from the beginning was always to develop these materials and be able to apply them at architectural scale. And in order to really harness the potential of these biopolymers, we need to consider multiple aspects in which they differ from traditional materials: the heterogeneous material properties, life cycles, and durability, but also the scale. So here we have an image of a print that was taken from the EKA workshop in 2022. And several of these demonstrators, including living prototypes, radicant cellulose enclosures from left to right. As we steadily increase in scale and scope, we move from the object to the system. In this case, our recent experiments have involved a series of prototypes for a biopolymer panel system. As a case study, we monitored how these panels react to environmental pressures, programming failures, and decomposition, and used this data to direct incremental repairs to the element via a parallel digital framework, which we term the history stack. So notable in this series of experiments with biopolymer 3D printing This is a biodegradable material. It is inherent in its nature to change, warp, stretch, and swell, especially when it's exposed to the elements. So the frequency with which we would be faced with the need for, in the instance of conducting some kind of repair or renovation, is going to be greatly increased. And with that, we have a greater need for more detailed and more flexible framework for storing data about these built entities. And we've broken that down into 3 basic parts: the aggregation of the data itself, so some way to store data about our built entity, an integrated way to analyze that data, perhaps extrapolating other data streams from more basic raw data, and then activation. How do we actually make that operational instead of it just being a logbook, a database that sits static and can be pulled out of the drawer every 20 years. We want to design a framework that can be actively used on a day-to-day basis by the stakeholders in a building or the designers and occupants of a particular built entity. If we slightly reword this and also include the implied intermediate steps in this hierarchy, we end up with these 5 key characteristics of what I've termed the history stack. Data semantics or semantic links for associating those different data points, analysis or the extrapolation of patterns from those links in that data, triggers some kind of way to assess when a particular condition has been met. So for instance, and I'll give some examples, but perhaps when a particular repair or renovation is needed, can we have a way to detect that directly from our framework instead of needing manual intervention? And can we make that automatic? And then actions, integrated protocols that use this data and maybe instruct us in how to make those repairs. The name of the history stack itself comes from the idea that we are aggregating this data continually. It's continually being stacked one layer upon another and always evolving and growing to incorporate new models. What that actually looks like in practice is, at its most basic level, a database. We used InfluxDB, which is a time series database structure, with some added functionality for scripting and conducting queries and inferring trends. So here on the left, you see a time lapse of one of our demonstrator observatory structures, where we've positioned a set of 9 of these biopolymer panels, and then basically surrounded them with a suite of sensors, both camera, as you can see in this time lapse, but also 3D scans, thermal sensors for temperature, also weather sensors for humidity, and then beyond that base layer of raw data, there is, as I've mentioned, the additional layer of extrapolated data. So for instance, if we take this image data, we can then, using computer vision, monitor the changing area, for instance, as you can see on the top right there, of these panels, as one way to monitor how these change over time. And as you can see from the time lapse, the material we're dealing with is highly sensitive to the environment. You can see as they warp and swell and as tears emerge in the structure. So we have a highly dynamic building system that we're dealing with, and we need a data structure that can accommodate that. So our history stack attempts to be as flexible as possible. An entry in this database can have any number of data fields, but we try to, oh, sorry, excuse me. And I'll fly through really quickly. These are associated with those semantic links. that allow us to extrapolate a greater degree of information. Finding those thresholds that will trigger actions such as repair, where we can analyze these. And then, for instance, here you see that we've 3D printed directly on top of these panels using a combination of 3D scan data. And the incremental nature of the history stack means that we can track features more robustly, and it means that we can immediately begin recording data instead of having to wait until we have the exact, most precise format for our data. We simply encourage to start building a database from the ground up, and we can later integrate that through these semantic links. So here you see how we've taken the daily 3D scans that were being taken, combine that with a much higher resolution fabrication model in order to extrapolate the warping data into the more high precision fabrication model. And just to wrap up, this history stack attempts to address the either too compartmentalized or monolithic properties of existing passports or digital building logbooks to create a more practical and interoperable system that's much more generic and able to encompass new models as they arise. Thanks.